And thankfully, Eloy agreed to present something that I thought I would be able to help to present, but I'm unable to. And this is this 1,000 or 8,000 brains, the 8,000 brains theory. There is a book and there's a paper.
Yeah, and this paper itself, so I actually made it more applicable specifically to 1,000 brains. But the paper itself talks about a framework that Jeff Hawkins and Numenta, which is a company in the Bay Area, have been working on to create more kind of biologically constrained AI. And I'll mostly go through that, but I also connected a little bit to 1,000 brains theory for people that are not familiar with it. So first of all, so the main thing that they want to talk about in this paper is basically to move towards more general AI, because current AI metrics or deep learning approaches are very narrow and they have very specific tasks that they're solving. And the idea is here is can we make a sort of like a computational model that is able to basically pick up on things faster and stuff like that. And what they're saying basically, especially at the beginning of the paper, is so we should be looking more at what ideas are coming from computational neuroscience to create something like that. And I'll preface this a little bit with, I'm not sure how applicable it is for us per se. I think the computational neuroscience ideas are really cool, but obviously we kind of do want to have narrow AI in a way, if at least like a narrow. It's good to have a narrow task for us because we're looking specifically at neuroimaging data, and I don't know if we would need something that is just like, you know, reasoning about everything. But it's still, I think, interesting. It's still interesting ideas, I think. So currently what they're saying is the approach that we have currently, these deep learning networks, even things like AlphaZero that have done really well in playing games and stuff, they cannot reach general AI fundamentally. And they also say that in order to at least try to bridge the gap, we should look more at computational neuroscientific ideas. And specifically, Jeff Hawkins is very much interested in the neocortex, and that's what Numenta has mostly been focusing on to like get ideas from, basically. So this is basically their overview of kind of what is going on with existing AI currently. So it's very much offline, batch-oriented learning. And once you've trained a model, it kind of stops. You know, you have to retrain it to do another task if you want to, which is not true for you know, humans, for example. You constantly are learning. If you've learned chess, you don't have to relearn chess if you learn tic-tac-toe. That's one of the examples they give. Second of all, I think humans do some supervised learning, I will say personally, but I think generally it is unsupervised. People just infer things from context, and things don't have to like specifically, we don't need like rewards for like, you know, like, oh, you said horse correctly, here's a candy or something. I mean,
Supervised is faster.
no, sure, yeah. I'm just saying, like, generally we don't need it per se. I think that's their point with like unsupervised learning. Existing AI needs very large training sets, and we have more of like a constant stream of sensory data instead of being put in a lot of different locations. So one thing they say that is actually a good, like positive thing of existing AI is that it's very distributed. So you can basically put it in anything. Like you can let it look at the internet everywhere at the same time. You can basically whatever you want. That's not true for humans because they're fundamentally embodied and they have limitations and they have a stream of sensory data that is constantly coming in, and that can't, you know, you can't just like be in another country, for example. Then there's things like fragility to noise and faults. So that's one thing they talk about as being one of the biggest problems with neural networks is that they're very fragile still. That, you know, if you can very easily fool a neural network if you want to. For example, with one example they give is like self-driving cars. There's been a lot of work from like MIT students and like other groups that have like tried to just like put a sticker on something and completely changes whatever the model is going to do. They talk about sparse representations basically and how they provide more robustness in the brain. So they say that robustness and this like sparsity is basically provides the robustness to the noise and faults that you may make if you're a neural network, for example. There's a large manual process to creating the system. So one thing they talk about is that the person that creates the neural network biases the neural network in the ways that it's creating it. That can be like either through the data that you choose or the way you basically put the neural network together, which we normally call inductive biases, stuff like that. Whereas in neuroscience, it's more of like an automatic general system, and there's not really. You may say that the person that births the child biases it, creates the system, but I guess if you're talking just about the brain, you don't really, construct it in a very specific way yourself. So there's no like, I guess.
Well, but there is a bias.
Parents do bias their children, obviously.
But I heard the bias versus like if you grew up, if your visual system develops in the steppes in the field, like prairies, versus in forests with vertical lines and stuff, like always in Amazon forests, like when there is always, I heard there is a different measurable, maybe it's a, crook theory or something.
Oh yeah. I mean,
but like there is a measurable bias towards vertical versus horizontal lines.
Oh yeah, no, that's actually interesting. I mean, these things are a little bit like crude, I think they're a little bit.
No, I mean, yeah, we're all trying to make our points.
Yeah. So the existing AI is super power inefficient, and that's not true for neuroscience.
Where is Amrit with his fly? Yeah, exactly.
My fly? What do you
Yeah,
mean
you
by
gave an example, very directly phrased, and it kind of stuck in my head, and that was something fly. Why it is so small and so powerful compared to what we're doing, and so it's a very good metaphor.
Yeah. Do you think that like the way that they're writing this out? I mean, I don't know. I mean, I feel like there's a set of observations, but I don't really understand where this is going. Maybe Eloy.
No, that's why I connected more to the 1,000 brains theory itself. I think this paper was a little bit kind of random, mostly. Like it was just like, oh yeah, cool. That's a cool idea. This is a cool idea. This is a cool idea. This is a cool idea, and that's it. It's cool ideas, and that's kind of leave you with that.
Aren't these distinct? I mean, we already know like what's the difference between a normal human being and a machine, and that's the difference which is stated here. I think the same thing that what Amrit said. I don't know. Are we actually going to train the same thing like as neuroscience, or like where we approach?
No, so the point I think they're trying to make is that if we want to go towards general AI, we should use the things that we at least are kind of aware of in biological systems.
Well, we are trying to attain that stage.
Well, not
anyway,
really
right?
though. Deep learning currently is very much focused on engineering, I think. Like transformers have no basis in anything in terms of like the brain at least, which is fine because it's a really good, so that's also what they say, right? They make a distinction. Narrow AI, there's nothing wrong with that, but if you want to go towards general AI, the way we're currently going with just stacking narrow AI on top of narrow AI on top of narrow AI, we won't reach what we're trying to achieve. So like transformers work really well for certain applications that you're trying to do, which is fine, object recognition,
Right.
But that's a very narrow application. It's not like transformers are the be all, it all of like general intelligence or something. And likely it's not, because the one thing that we can look at and say this is like more general intelligence are animals in the brain, basically.
And Jeff Hawkins in his talk, he always says that to have a true intelligence, we have to do it. He says that it's not a. Can you hear me?
It doesn't work.
What did you say, Ashkan?
Yeah, Ashkan, can you repeat the last part? We're just having trouble every time. We can't hear because of the system.
I'm saying that Jeff Hawkins in his talk, although Jeff Hawkins is not in this paper, I have no idea, but in his talk and his even books, he talked that he believes that to have an intelligent AI, that is the only way that we can go. the goal.
Yeah, he's a very
I
big
mean,
fan of the biological.
yeah,
And so
he essentially
I
says
think-
that otherwise it is impossible.
Yeah,
Yeah,
and I
so-
think one thing that I think is interesting, we had a little discussion about this last week. I also don't think he's trying to say like we can like fully reconstruct the brain. I think what his point is at least is that we should lead off of a lot of like the mechanisms that he at least thinks are currently happening in the brain.
Actually, he says that. He says in his, as I said, if you listen to him, he once actually says that we want to decode the cortex completely. And
Yeah, that's
even
true.
he for his company, he says we have two goals. One of them is decoding the brain completely. The other one is using those information for the AI, right?
Right,
But
to
he
reverse
mentions
engineer.
it. Yeah, he mentions it. The second one is a distant aim. And he himself hasn't worked actually on that for a while because he thinks that we have to first understand, decode it completely. So he,
No, true.
he mentioned,
I think at least in this paper with the HTM they're building, so that's more what I was talking about. They're trying to constrain what it does based on our sort of like computational neuroscience knowledge. And yeah, he specific in this paper, they also say, so it's not written by Jeff Hawkins. And the reason why I'd say it's a little random is because they have published a bunch of papers and they've tried to kind of like get it together in this paper together. So it's more, I think, based because the reason why it's a little random sometimes is because they have a lot of stuff that they want to discuss and only a limited amount of pages that they want to discuss it in. So that's why it's a little bit of like things that seem kind of out of nowhere. This paper is specifically about HTM, which is hierarchical temporal memory that they were working on and that they've like sold to companies. But yes, I think the goal for Jeff Hawkins in the end is to reconstruct the full human brain. I think the way they currently think is the most effective way though, is to do it kind of with like to do it based on kind of these constraints, these more broad ideas, like things like highly power efficient, like, you know, sparsity in the activations and the representations, and embodied reasoning. So they use more of these like broad ideas to try to get at least a model that is a little more general than current AI methods. But yeah, I think, like you said, I think the goal in the end would be to be able to fully. He talks about reverse engineering the cortex a lot, so I thought that was funny based on our previous conversation last week. Okay.
Okay, just before you move on, one sec from that slide. I like some of his ideas, but I don't really understand the automatic general system. Isn't the brain incredibly structured both microcircuitally and macrocircuitally? So it is.
Yeah, that's actually one thing that he uses to create the 1,000 brain theory. I think what he means by automatic and general system is more that, let's say you have a neural network that can do like a classification of cats and dogs. That's manual, right? You need to like get the data, you need to put that into the system, you need to learn it. Whereas like a human or a brain kind of like walks around and it automatically learns general stuff about the world. I'm not saying that I agree with that per se 100%, but I'm just saying that's, I think, his difference between automatic and general versus manual process.
I see.
So
okay.
like a neural network won't emerge or something, but representations will, in a way, if that makes sense, like in the human brain.
Got it.
Yeah, it's a little bit, marketing and selling, calling the brain an automatic general system, I think is a little bit too far, but.
I feel, I don't know, when we're talking about this neuroscience thing, we're talking about the whole pipeline, we're talking about it's taking the data, processing it, predicting like whether it's like a dog or like even as I go, unsupervised, supervised, whatever. But in existing AI, what we are talking about is just like one specific part of that pipeline, which is like just predicting it. Yeah, we are not even talking about like how that data is actually coming with, and I feel that's like that is what I could understand from at least from this table, because our brain is doing our brain is doing everything in just one go, but we're just talking about one specific part of that.
Right, and neural networks won't emerge or something.
Yeah, so
it's very specific. You need to try and like fix the loss function, and there's a lot of like engineering basically that goes on. Whereas our brain currently, need to like fix someone, you don't need to change their loss function or something for them to learn representations.
Because like right now, even right now, like a lot of research which is going on which takes everything into account, be it speech, be it images, be it natural text or anything like that. Everything collectively, and then you're doing something, either predicting or either reconstructing the speech or predicting something. So that's still going on, but then that process is just like one part of that pipeline that our brain does.
Yeah, exactly. Yeah, and it's very manual. That's what I mean.
It's very
you
manual.
have to like find the correct data, you have to clean it, you have to whatever. So.
But then look at it like this, right? Even in our brain, if you want to do something manual, then we'll have to do everything just like what we're doing in existing AI right now.
Yeah. So some of the important aspects that they talk about is like, what is intelligence? And their answer is that human intelligence is the brain's ability to learn a model of the world and use it to understand new situations, handle abstract concepts, and create novel behaviors, including manipulating the environment. And I think the latter part is also very important, which is most current neural networks don't do, even if they're doing reinforcement learning. It's a very like constrained environment. And the idea here is that you have a model that can learn a model of the world without needing any explicit inputs, and also can start to manipulate the environment. And they don't show that in this paper because it's obviously still like very much in the early phases of like, at least the last part, the manipulating the environment, they don't show.
But this kind of reflects the development of our philosophical thought.
Yeah, this is the philosophical.
Yeah,
part of it.
well, how we think about learning in intelligence. IQ tests, schools, very structured environment, very specified requirements of what you need to know, what you don't need to know, how to test you, and things like that. Only now people, well, not now, but recently became more vocal, converting into, well, creativity is important. Creativity is another word like AI. It means nothing. What is creativity?
Yeah.
And what is intelligence? And we don't know how to measure it, and we're like struggling. And
I think though in like philosophy, this has always been more of a fundamental. I think in terms of like practical in society, we've made it very,
reinforcement learning.
right, strict and like very like these are the metrics and this. I think generally, even if you look at like the Greek philosophers and stuff, I think they had like a very broad sense of what intelligence was.
Yeah, but like how to measure it is
Right,
very
exactly.
difficult. That's why we formalized the tests and whatever.
And so two important aspects here: sensory motor integration, which means the integration of sensory processing and generation of motor commands, is, according to him, essential for intelligence, or according to the authors of this paper. And that also goes together with embodied reasoning. So these sensory motor mechanisms, they basically shape our ability to do abstract reasoning. And I think one cool example of this is that they found that when people are doing geometric manipulations in their head, there are grid cells that fire, and grid cells are cells that know this are kind of like fire based on the location that a person is in. But those grid cells also fire when people are doing mathematics in their head, which is interesting because kind of you can imagine that the way your brain represents the world and thinks about it, that also flows into other fields. Like when topologists maybe are thinking about mathematics, they think about the space in their head and they kind of move through that space, maybe similar to how humans would move through like the actual world. It's very hard to say if that's true or not, but I found that an interesting result that people were finding that when people are doing geometric manipulation in their head, they have grid cells firing. So it seems like throughout space. Okay, current AI. So I got a few quotes from their paper. So they're saying that current AI is almost independent of environments. It's very much kind of like very restricted. You get input data, you predict output data, but there's not really a lot of interaction with the environment. It's very much tailored to the algorithm. You give it specific type of data. It needs to be 64 by 64 pixels or whatever, stuff like that. Typical AI systems do not learn anything after training, no matter the type of algorithm you use, learning algorithm you use. They also talk about continuous learning, that it is like a part of of deep learning, but currently, especially with backpropagation, you have a fundamental limit basically, because you have to do like some sort of like a discrete forward pass and backward pass, and that means it's not really continuous. It's more like you're just still training, kind of like it's, you know, there's very different. There's a big difference between kind of continuous learning and having these distinct phases of like forward backward pass. And then also narrow AI performs one well-defined task in a single way. So that's what I talked about before as well. That it's like very much.
But it's worse. The situation is worse than that. And I'm borrowing a term from someone. Obviously, they're not only narrow, single domain, they're ballistic. Like there is no computation thinking happening when a neural network is applied to a sample.
Mhm.
It's like every sample takes exactly the same amount of multiplications and additions, and the result is produced. Every sample, regardless how easy or difficult or anything, it's just like a cube. Sample in, prediction out. There is no like, okay, wait a second, let's think of it. Forget about wait a second, let's collect more data. This is not even like in the loop.
So some of the limitations of narrow AI, they also talk about the pros, but I thought it would be more interesting to talk about kind of what they're doing in their model. They're greedy, brittle, opaque. That's some big problems that we're struggling with as well. They lack abstract reasoning abilities and possess common sense about the world. That's not something we're struggling with per se. I don't really need a model that do abstract reasoning when I'm looking at dynamics of fMRI, for example, but it's still cool. And then narrow AI is a proxy for the person that made it. I think we talked about that before. Murnell also talked about. So it's like, you know, it really depends on the person, kind of what type of algorithm you finally get for neural networks. And that, although obviously the brain is kind of made by a person, and there is definitely some bias that gets, you know, there's like nurture and nature. Both are influenced by the person that you were birthed by. That doesn't mean that it's literally a proxy for the person that made it. So, you know, it's like you can still also create other ideas. You can become different than what your parents intended you to be. I think that's kind of what they need. Then, so Jeff Hawkins is very much interested in the neocortex, and he says that it's a very important way of starting to look at biological constrained AI. So the neocortex, the neurons in the neocortex, each neuron has about 1,000 to 2,000 synapses, which is obviously very different from the current point models that people often use in terms of their neural networks. Each region, you can have obviously 1,000 connections to other neurons, but each region operates according to the same principles. So this is his idea of there's a common cortical algorithm, which is an idea that has been voiced around in the computational neuroscience community. Basically, that although each region does different things from like a representational perspective, let's say language or sensation or stuff like that, the low-level computation of small sets of neurons in a cortical column is very similar to each other in terms of the computation, but the representation that you get from that sort of computation is different per region, because each region has a different thing that it's looking at. Basically, that's his idea. And there's hierarchical, horizontal, and feedback integration, which you also don't see in neural networks that much currently. So this is the idea, basically. This is the visual region, for example, and this is your sensory region. What happens is that each cortical column in that region creates a sort of like slightly different representations of the same object, because they get a subset of that object. So let's say if you're looking, the top part of the mug is in the first 4 columns, and the bottom part of the column is in the last 4 columns. But these columns they talk to columns to each other within a region, but also to columns in another region, like for example, the sensory column. So let's say the tip of your finger is one column, the tip of your middle finger is another column, the tip of your thumb is another column, et cetera, et cetera. And the main idea is that each have an allocentric reference frame. So they know where they are in space. And so then when you, let's say, when you touch a mug with your finger, it communicates to your middle finger, kind of the sensation. And then because your middle finger knows that it's close to your index finger, it knows that it's almost going to touch it, or that it's going to touch it when you do a certain motion. So that's why it's called 1,000 brains, because they're basically saying each cortical column has this sort of reference frame of where it's at currently, and predicts what it would be like if it would do certain actions, each column independently. And they communicate about what they see and feel. For example, one famous thing he says in one of the talks that he gave about 1,000 brains theory is that, let's say you don't know what an object is, and you put your hand inside of a black box and you try to find what type of object it is. Your whole hand each finds like a different part of the mug, for example. If you don't know it's a mug, but let's say it's a mug, it puts it on a different part of the mug. But then together they kind of vote what the object is based on what each region has felt. So you basically see each as independent blocks of information. And then these cortical columns, they basically vote together to say, okay, we think it's most likely mug. That's one of the examples he gives. So that's 1,000. Does anybody have any questions about this?
Okay, it literally just sounds like they sat at like a coffee table and just made up this example.
What?
Like a coffee mug. But I don't really know. Like even when you had that comment before with the grid cells and the mathematics, I feel like there is like very specialized circuitry and it's just used somehow for multiple tasks. And I'm not super fan of like doubling all the computational areas, because it's not clear if that's what's happening. I don't know. What do you think about this? Do you really need this much computational hardware to synchronize your retina?
I think in a way it's very simplistic, but I also find it hard. I wonder, so I think your question about this sounds like a lot of computation is very valid. I don't know if this is a lot of computation though. It sounds like it is. I just don't know. If you use only sparse representations and sparse connections to other neurons, it could be efficient, I think, even if you do it like this. I also agree that it's a little bit, that's what a Dutch saying is, short through the corner. Like it's very simplified, I think.
Like, for example, I'd imagine, let's say like you were doing the place cells grid cells example of, you know, spatial navigation. You could have visual input, you could have tactile input, right? Coordination. And I'd imagine, okay, you have one grid cell, you know, computational area in the hippocampus, and somehow, you know, no matter if it is a visual stream or, you know, a touch sensory stream, like it somehow would be coordinate data transform, but then put into the same hippocampus circuit to get the output. So that's how I would look at it, rather than having.
He's actually only specifically talking about the prefrontal cortex, or the neocortex.
Oh, okay.
Yeah,
but yeah,
because one thing that I do know from computational neuroscience is that they have found that a lot of these circuits in the neocortex are like very similar, like the pyramidal neurons.
Yeah,
they seem very like kind of to have the same structure, at least in the neocortex, a lot of it. And so his idea is basically, it seems like they're all doing kind of the same computation, but maybe the input is just slightly different. And that input, by the way, because I do agree, there's a lot of subcortical structures that are very interesting, but they basically decide which part of the neocortex to look at which part of your input. So let's say your hand, subcortical structures only funnel through information about the index finger to a certain part of the neocortex, and but they always do it to that part of the neocortex. But the computations that they make, depending on whether it's a thumb or an index finger, those are the same. It's just that they all have this reference frame, basically, and the neocortex does this computation to get a representation back from the input signal of like the scale, for example.
He's kind of relentlessly repeating that I'm talking only about neocortex.
Yeah.
And he's also like, spread out the neocortex at the table. It's basically uniform napkin of exactly the same
Yeah,
structure.
and it's
everywhere.
very simplified because I mean, subcortical structures are like essential to the human brain. I think he mostly is talking about like abstract reasoning and higher order function because that's generally attributed to the neocortex. I don't know. It doesn't make sense. I mean,
this view matches a little with some of the observation, because even I think in his talk there is a recent study that found that there was a woman who lost all of his language region, but she was bilingual. So, and the question was, well, if that region is not, how can she do that? So there are a lot of studies that have found, okay, you can retrain different part of the brain to do different things. And I think we know even before that cerebellum, for example, is almost like a smaller cerebellum is like a smaller cortex, right? And it actually mapped exactly what the whole brain does as a smaller scale. So this observation is actually old. So, and he talks about it in one of his talks that, oh, these are observation that matches this view.
Interesting cerebellum observation, Ashkan. Cerebellum has about 5 times more neurons than the rest of the brain. Its size is smaller, but it has so many folds. It's so finely folded. It's literally like 76 billion against 16 billion.
And we cut it usually, so because it's not in FOV. So.
Yeah. So I mean, my personal opinion on this is that I think it's cool. I think it's important for people to establish these theories, and I do think it's an interesting theory. Is it true?
Conjecture. I mean, so yeah.
Yeah, I know it's a conjecture, exactly. It's very much, I mean, I can't say whether it is or isn't, or whether I fully believe it or not. I do think that some of the things he talks about later in terms of like and putting it into his model are interesting because they are more, well, things of what we actually know about the brain. This conjecture, I mean, they're researching it now. I will probably need to see more evidence than I think is currently out there. I do think it's interesting though. I think it is, at least it gives us something to think about in terms of like what could be happening, but we need to be careful to just be like, oh yeah, this sounds reasonable, so we'll just accept it, because that's not, it needs to be supported more. Okay, so I'm just going to go back a little bit into his model again.
Or we can apply Jeff Hinton's method. We tried it, it works. If this works, then we don't need anything else.
So back to his model, basically, that they talk about, or not his model, but the model of Numenta that they talk about. So, okay, so they want to have these 3 data structure properties, and they also have some algorithmic properties. I think I forgot to put a slide on that, but I'll just explain it. So the first 3 data structure properties that they want to have, the neocortex in data constrained AI is what they call it, is a sparse data representation. I think I talked about this before. So yeah, if you think about it in terms of binary code, it should be a few zeros and mostly a few ones and mostly zeros. They say that we need to have a more realistic neuron model. Currently, we just have mostly like feedboard and stuff like that. But in the brain, you have hierarchical feedback. You have feedback from neurons that you send to as well, and your feedback from neurons that you are sending to you. And that there should be reference frames. And this reference frames part is based on 1,000 brains theory that I just showed you guys. So how is the neocortex built up? Generally, it's built up out of cortical columns. So they just showed a bunch of cylinders. Yeah, sort of like this. This is in a single region of the neocortex. Each of these cortical columns has 6 layers, and you should take layers not very directly here. I think because it's hard to really put them into like separate layers. They're so interconnected that it's like, it's really hard to make a real distinction of like layers. There are 6 layers, but it's very much not the same as in deep neural networks. Very, very different. In each of these layers, there's a mini column. So this is within one of those layers. And they have, these are, for example, the neurons in one layer.
So no lateral connection between
Okay, so
columns?
they leave out the connections in these figures. They are also like simplified figures for the model that they're describing, but they say that it's like kind of similar to like how the brain is organized. I'll talk about the lateral connections later. So I've been talking about this a little bit, but the hierarchical temporal memory model wants to kind of put these data structures and some algorithm structures into this model that they think are happening in the brain. So it's based on the 1,000 brains theory, and that's where the reference frame comes from for these cortical columns. They basically use some broad ideas in the computational neuroscience community and for like this more general computation framework. And they mostly base their structure, the structure of this hierarchical temporal memory off of pyramidal neurons, which are very common in the neocortex. So first off, sparse, I kind of said this before, but it just means like a few ones and mostly zeros. This would be a representation for a zebra. So it's furry, it has 4 legs, it's striped, it's black and white. Generally, people already know that it's not a zebra if you have that as a representation. This is what it would look like in one of those layers that I just showed you. So only a few of them are firing, only a few of them are ones and the rest are zeros. Then the second part is the realistic neuron model. So this requires a little bit more explanation. So you have, so these are the neuroscience terms, but you have apical feedback from neurons that are above you. You have context feedback from, and you have feed-forward feedback. So currently in most neural networks, we just have feed-forward feedback, and we go from the lowest level to the highest level. But essentially what they're saying is, and we know this is true for pyramidal neurons for sure, that there is feedback from neurons that are deeper in the network that feed back into lower level neurons, but there's also lateral connections, so context connections, and that we don't have those in current deep neural networks, as you can see on the left, because that's basically what they do. So to kind of map them to each other, so the soma in our point neuron model in deep learning is just a sum of each of the feed-forward connections or proximal connections, and the axon is a nonlinearity, which would be here. And in this case, what we have is a soma. We have multiple higher level feedback connections that are already combined in some way. The same goes for the context connections. And we have one single feed-forward connection, and they're put together in the soma in some type of way. I mean, we know it's a fairly nonlinear system, so it's not just a sum, but yeah, so that's their idea of a realistic neuron model. It's definitely more realistic than the point neuron model. That's definitely for sure. Okay, and then reference frames. So I kind of talked about this before with the 1,000 brains theory, but changes in movement are mapped to locations in the reference frame. So if I change my hand, then kind of this representation of my hand changes in terms of those reference frames. Every column maintains an allocentric frame models of the object it senses. So like I said before, if I touch the mug, each finger, for example, has a different column that is associated to it, and they all maintain their own little allocentric frame model. So to come back a little bit to what Amrit was saying about it takes a lot of computation, you can also view it kind of as like, if you only do small updates on your allocentric frame, you can also say that there's actually very little computation, at least the computation stays kind of the same throughout time and doesn't change as much. Because if you think about how the brain would implement this differently, if it needs to like just kind of do like large scale computations, if you want to kind of query it or something, if you want to like, okay, this is a cup, if you don't constantly update it, and you would have to update it just at the moment that you're thinking about what is this object, that would maybe require more computation. If that makes sense. Because the way they explain it is like these cortical columns are very small, complex, like specific circuits, but they're also very efficient. So, you know, it sounds like a lot of them, but if you do it in a distributed manner, it could be very efficient. And so this is an important part because I think they haven't shown that this exists yet. I think I've seen 1 or 2 papers where they try to show this, but they say that locations that you give to these cortical columns are based on grid cells. And so we've seen grid cells in the Neocortex, but they also say that there may be cells in the Neocortex that are doing this. So yeah, they call them displacement cells. And I think they've published 1 or 2 papers on the fact that they exist, but I think it's still not really, there's not really like a full agreement that it's true. So yeah. So let's start from the beginning. Again, the HTM neurons. So how do they do sparsity? So the semantic meaning of a representation depends on the input, and nearby bit positions represent similar, not positions, but similar semantic meanings. So if I go back to this one, black and white are closer together basically than things like furry, which is a more abstract thing. So yeah, things are more similar or closer together. Then I showed you this already, the more realistic neuron model. But so what they say specifically is we must be able to incorporate apical, basal, and proximal feedback. And a neuron in their specific model, because I'm not specifically talking about their model, there are 3 states: active, predictive, and inactive. Active is just 1, inactive and predictive are both 0, but predictive puts the sort of the cell body that they model into a prime state. And the idea is that each neuron predicts its future activations. So it moves into a predictive state based on the basal and apical dendrites, so higher order feedback and lateral feedback. And it determines whether it's going to fire in the next time step, because it's a very temporal model, basically. So if it's in its predictive state, it thinks it's going to be active on the next time step only based on its apical and basal connections. So how does that work? So let's say you have the state of the time at t-1 of a network, and a network is multiple neurons. Some neurons will move to their predictive state based on the current state, and that is because the other neurons will send the fact that they're active to the neurons that they're connected to, and those neurons that they're connected to will just decide whether they think they're going to be in this active state for the next time step t. And then predictions are based on the feedback predictions for higher levels, basically. So that's also how their learning works, because what they're doing is they're learning by reinforcing connections that are consistent with the predictions. So if so it's fully connected. Essentially, it could be fully connected. But they only connect to neurons that are active at the same times as they are. How does that work? So they have connections that are either 0 or 1, and they have a threshold, and it's kind of like how many times they fire together. So it's called the permanence value, and anything below 0.3 means that the connection is off, and anything above means that it's on. But so if it's a very long-lasting connection, it's harder to turn it off than if it's a short-lived connection. That's basically the idea. So if you've been, activating together for like the longest time, and then there's like a mismatch, that doesn't affect the connection as much as opposed to when you've just made the connection and it turns out it wasn't a correct connection, then it will switch off again. They don't talk a lot about the actual implementation of these things, but
So there's like a time period in which they can switch back.
well, it's more like if, so you can, I view it more as like a dynamic system. If you guys, you guys have been firing together, you go up. And then if there's a mismatch, you start going out of phase with each other, then you start, your permanence value goes down until the connection switches off.
That's really interesting.
That's their idea at least of an implementation. Okay, second part is the sensory motor integration that they want to do. So they have two layers. The first layer, the input layer, combines sensory and input location. And again, here they assume that these cortical columns know about the location in like reference frames. So that's an assumption. And then the second layer converges to a stable representation based on those sensory and input location data. So they integrate information over time as sensors move relative to objects. So if you have a reference frame of like a cup and you move your hand along the cup, you integrate that information over time with respect to the representation that you output, and the lateral connections between columns communicate about the information in different locations. So it literally is like you have 5 fingers. These fingers, at least in your brain, the cortical columns that represent those fingers are kind of talk to each other about what they see in that location of the object. So as an example, if we observe a boat, each cortical column sees a different subset of the boat and are in different locations in the hierarchy. So although their general computation is similar, at least that's what they say in this paper, their representations will be different because they get different inputs and they have different inputs from other neurons. So it's not just the sensory input that's different, but it's also the input from other neurons that's different. The representations, so like I said, this is also partly because of the communication through traversal connections. So how does that work? Yeah, so these are 3 connected cortical columns in a region. The layer generating the location signal is not shown. That's because it's still kind of, yeah, they're still trying to find that, I think. So there's some changes with sensor movement. Some of it is stable. So let's say the color is stable. And you send the changes with respect to the sensor movement, basically. So this is like kind of, it's a very general picture of how this would work. So each of them gets sensory input. Each of them gets location input. That's this one. They communicate with each other throughout the layers. So you have 6 layers. And then they also communicate with the highest layers. They communicate in terms of like, I think it happens in multiple layers, but at least they communicate with each other about different parts of the sensory signals, because each of them gets a different subset of the sensory signal. And I think that sensory signal and what part they get, that's all done by subcortical structures. So they don't talk about those specifically, but yeah, I think that's the assumption. So they've done simulation results with this model, and they found that the network functions even when 40% of the neurons are off. So they manually just turn them completely off. Or no, if it's 40% sparse, basically. Learning converges to a stable representation for different inputs. And they achieve comparable accuracy to other sequence learning algorithms, including statistical, feed-forward, and recurrent networks. So
but I missed how they trained it. Sorry.
I think it's mostly sequence learning.
But like, is it still gradient based?
No, so it's completely based on this like local Hebbian learning rule, where they determine based on how often they fire together, whether the connection is going up. And it's everything is 0, 1. So it's all binary basically, because both the activations are binary
like a
and the
Boston
connection.
machine.
What?
Boston machine.
How
Just more similar, yeah. Yeah, I'm right.
how are the neurons connected? Is everything connected to everything, or is it random connection? Sorry if I missed this.
So what they do is they learn the connections. That's the idea.
Oh, okay, right.
I think, yeah, everything can be connected to everything. It's just that a lot of neurons in a single layer will not every all the neurons in a single layer will not fire together all the time, so they are not fully connected, I think.
I like this predict thing. I feel like, I mean, I don't fully theoretically understand it, but I feel like it sounds similar to like the forget gate with the RNNs.
Mhm.
But there's this idea of some sort of, I need to, memorize now something about.
I like that
Current.
too. I think it's also cool because it's like more of a heavy and local rule, and
Yeah.
it also helps with constantly learning because you have a very local rule. And although we do have kind of like a local rule in gradient descent, you do need to keep because it's like so hierarchical gradient descent, the updates, they are dependent on deeper layers in your network. So you first need to compute it there to compute the what's it called again? The local gradient that you have for your neuron. And this is purely local almost. You basically just kind of predict what's going to happen to you in the next phase, and then you just update that constantly. It's just kind of constantly happening for whatever input you're getting. So it's a very sequential network in itself. Yeah, so that's simulation result. I'm a little bit skeptical of these results because they also talk about like, oh yeah, we implemented it on an FPGA and it only uses 225 watts, and you can't do that with neural networks. And that's not entirely true, because if you sparsify your neural network and then you make it like much smaller and you only use 8 bits, for example, to represent the weights, you can still put it on like embedded devices too. It's not the same as this, obviously, but I just thought it was a little bit like obviously you can't train, like for example, AlphaZero on an FPGA, and it would use huge amounts of energy, and that's definitely a huge advantage of this method specifically. I think it's also because they only use binary values, both for the connections and for the activations. But I just thought like you could implement it on a smaller device. I don't know about AlphaZero, but I know a lot of at least like visual, like CNNs and stuff, you could do that with. Yeah, so what they say is like we found basically that multiple columns work together to minimize the number of sensations needed to recognize an object. And with sensations, they just mean like sensory inputs. So because these neurons, so you see it as like time steps. So you give it an input for 10 time steps, for example, and over those 10 time steps, the activations kind of converge to a single representation in each layer. And that's what they mean by they minimize the number of time steps basically that it needs to recognize an object. So if you give it an object for 10 time steps, it will slowly start to like converge. And then when it converged, you can, for example, do a prediction of what the object is based on that representation. I think that's what they mean. So it's in a way, there's a lot of similarities to me to like Hopfield networks a little bit, but it's much, it's more complex.
Well, it's just the training, right? The
Yeah.
mechanism.
Yeah, the heavy learning, I mean, yeah, so.
Yes, on the topic of Hopfield networks, so my whole issue with this paper is like, it's awesome. Maybe the brain does have multiple models in it for the same kind of object. And it speaks to this idea that the brain isn't really a function, it's more of a mapping, that's awesome. But they use all of that to pitch this architecture that, first of all, they're vague about. And second of all, reads, just from what I see, like basically a fancy Hopfield network. And I really, and especially because this is coming from a private company.
Yeah.
By doing that, even by having like a section on the commercial use,
That's
I lose all trust in this paper and even the idea of 1,000 brains. Like they're gonna have to, like, in order for me to regain that trust, I'd have to see a lot more evidence. Like I don't.
Yeah, but so they do, okay, so let me say real quick. So they do publish a lot of papers, neuroscientific papers, that are more actually neuroscience papers and in support of 1,000 brains theory. And I know it's a little biased that if your boss is paying you to research, 1,000 brains theory, that you're likely going to come up with papers that prove that instead of disprove that. But They do, I mean, this paper, that's why I said, this paper feels a little random because it's so much of the stuff that they've been working on combined into like one sort of like seminal paper is what they're trying to say probably. But I think there is also more, there is some actual neuroscience work that they do.
It is interesting that Jeff name is not on this paper. So I thought, because Jeff when in his talk he says that building the deep learning thing, building the model is a distant second aim for that company. He says the main goal of them, at least for the time that for that time that he was talking, he said for now the main aim is decoding the cortex, not building an AI for now. So I wonder if that has gone to the reason that his name is not on this paper. So because he always says that we have to go first, try to have a very good decode and a very good model, right? And another thing is that it seems that they use for evaluation, because they are a private company, they use actually a lot of third-party collaborators for evaluation, and they actually work with Allen Institute. So. Another point is that actually I didn't find how they make money. So
no, that's actually what I was going to say. I think the point actually is the reason why they're pulling this as like a biologically constrained AI is partly because it just probably makes more money. If you are able to have like a model that you can sell to companies, that's a way to make money to do more research on, because the idea of this is that it's going to be like a model of the brain, but they also need it to be applicable to things so that they can make money off of selling these things to companies, I think, partly.
Yeah, it's the power thing. If they can manage to do that power, it's really good. So
that's actually how it reads to me, is essentially like kind of a marketing.
Yeah, I think it's partly is, yeah.
Profile.
That's also why I wanted to connect it more to 1,000 brain theory, because it's very hard to understand this. It seems more like you said, like you said as well, like a marketing. I think I understand what they're getting at with this. And yeah, I also agree with GJ that it's still funded by the Palm Pad money that Jeff Hawkins made previously.
Yes. It's all philanthropic. I mean,
Are you sure?
Yes.
In their commercial use section, you don't think they make money off those partnerships?
I do think they do.
I think they do.
I think it's both, by the way, just FYI.
Oh, sure. I'm sure.
No, I don't think they're profitable or can be profitable.
I think they make
No,
revenue.
that I agree with. Just from the commercial part,
Not
they do
for
make money.
this, for previous, maybe that's what CJ.
But they do talk about some big companies. They're not like small companies per se that they work with.
Yeah.
They sell.
But they consult that or something.
No, they sell this method.
I think they do. Yeah.
That's literally what they say. They say like, oh, they're using it for fintech.
Yeah, there's 3 companies that they sell to. One of them does anomaly detection networks or something.
No. I agree that it's not profitable.
But they have revenue.
Yeah.
TJ, I'm just saying they probably get some money from those companies.
Yeah. I mean, them having revenue and not being profitable just means maybe they're not good at being a company.
Well, that's why they
They're not a
probably
company.
need. That's why
they're
they
research institute. Funded by Jeff Hawkins' personal money.
he says he always says that we are research. We are
Yeah, they do a lot of research. I mean, I think they try to make. So it's the same as DeepMind, right? They sell some of the research to make more money. But they're still a research institute, right?
Well, I mean, DeepMind is funded by Alphabet, which gives all of their money for research. They just do creative financing to be able to be profitable after AlphaGo, as they spun off 3 other companies.
Yeah, no, exactly. Yeah,
they don't actually make money. They might have some revenue, but they're not profitable. They burn so much money.
DeepMind more is about Google has so much money.
No, I know, but I'm more saying like, I think DeepMind does also sell some of their stuff to other people. And it's probably to make at least a little bit of, extra money. And I'm not saying that they make them profitable at all. I don't think they are for sure. And I agree that it's.
Well, just pay the bills, like.
And they don't do empirical studies at all. So no data is for them, which is they say that it's actually cheaper that way. So all of their empirical validation is done by their collaborators, they call it.
Right.
At least Jeff Hawkins. So they don't get. They're not. For example, they're not acquiring.
Well, like non-profit research institutes make a lot of money because they need to survive and pay the bills. but they're not profit, they're not making it for profit, just for survival.
Yeah.
And there are
Really
10
think
people
so?
in the lab. There are only 10 people in that.
Any
group.
nonprofit
Okay?
organization, that's.
No, are you sure? I think Numenta is an LLC.
Nonprofits just like nonprofits and corporations are just ways of managing taxes and liability. It doesn't really say anything about your bias.
I think it's
I mean,
incorporated.
No, but I mean, the same about universities. I heard here that papers coming from academics are less biased than paper coming from researchers that are not in state-funded universities. We're all biased.
I think that's ridiculous. I think
agree
everybody
that
has
you're biased
bias.
equally, but at least you can see where the money's coming from. That does help with public things. I mean, you can see everybody's salary and stuff literally from the NIH. and stuff.
Not in the private universities like
No,
MIT,
not in the, no, exactly.
the
That's
most
true. That's true.
highly published
No,
places.
sure. I mean,
So,
it's not a
that-
perfect system either. I'm not, that's not what I'm saying. I'm also not saying that that they're just publishing good papers on 1,000 Brains theory. They need, but they work on that a lot because Numenta is working on 1,000 Brains theory. That's more what I was trying to imply, not that they are like forging results or something.
Yeah, I don't think.
Because I think a lot of their papers actually, that's what I was trying to say to Noah, I think a lot of their papers are actually very convincing. I don't think that it's like currently considered like the full brain theory yet, but I think they are publishing a lot of good papers on 1,000 Brains theory. And no, I didn't mean to imply that they are.
Yeah, well, it's just, that's how I heard it, but I will have to disconnect or I will stop the recording and like you're welcome to continue discussion and everything, but I have to wait. Thanks everyone who joined and thanks Eloy for fantastic walkthrough.